We talk about artificial intelligence using the language of software. We imagine it as weightless, instantly reproducible bits, constrained only by the quality of the code. That illusion shatters against physical reality. Every single token generated by a language model is a highly specific thermodynamic event. A token is the basic unit of data a model processes, like a fraction of a word, and producing each one requires measurable electrical energy to execute thousands of matrix multiplications. Data centers function as massive physical energy concentration hubs. Within their racks, AI models operate strictly as structured energy flows. We are not in an AI arms race. We are navigating the most consequential civilizational phase transition since the printing press. For decades, our primary constraint was information. We solved it. First the internet, and now large language models, have made data retrieval and reasoning effectively free. But running that free reasoning requires massive, concentrated physical energy. That is our new absolute constraint. Running infinite reasoning on a finite power grid, guided by fragmented institutions and misaligned market incentives, produces acceleration toward a physical wall, rather than widespread abundance. This equation defines any civilization's capacity to function. Civilization capacity equals energy times intelligence times alignment. Energy is the capacity for physical action. Remove it, and the system stagnates. Intelligence is optimization and problem solving. Remove it, and the system loses direction. Alignment is the synchronization of intelligence and energy across time. Its absence turns high energy and intelligence into compounding fragility. Currently, the tech industry optimizes for intelligence, treating energy as external and alignment as secondary. In a multiplicative system, neglecting any variable restricts total capacity, creating a structural ceiling. This chart maps the rate problem. The immediate crisis is not a global lack of absolute energy reserves. It is a severe mismatch in scaling speeds. Intelligence demand grows on an 18-month doubling curve, while physical infrastructure scales on a slow, linear trajectory. Grid inertia cannot be bypassed with better code. Planning, permitting, and building transmission infrastructure takes 10 to 15 years. You cannot compress the construction of thousands of miles of high-voltage transmission towers into a quarterly earnings cycle. This means that measuring total megawatt-hours produced globally is useless. An intelligence-based civilization requires a much more specific metric. It requires energy quality. AI demands energy that is highly specific, consistently stable, and physically proximate to the data center. The first constraint is entropy. Entropy measures the degree of disorder or unusable energy in a system. Data centers generate massive amounts of high-entropy waste heat. It is physically real energy, but it is entirely useless for further computation. The second constraint is firmness. Training models can sometimes be paused, but inference, the phase where a trained model actually generates real-time responses to user prompts, is highly sensitive to latency. Intermittent wind and solar power cannot support it without massive, stable baseline power backing them up. The third constraint is geography. Generating abundant solar power in a remote desert is meaningless if you lack the specific high-voltage direct current lines to move it to a compute hub. We are stacking exponential compute ambitions on top of linear, geographically locked infrastructure. Inflation, supply chain seizures, and grid warnings are the visible downstream symptoms of this physical mismatch. Treating AI as weightless software has allowed massive, fragile physical dependencies to accumulate entirely out of sight. Behind every chatbot is a physical supply chain. It requires ultra-pure silicon, specific rare earth dopants, and European lithography machines. It requires a massive physical extraction layer spanning thousands of square miles. The critical minerals necessary for battery storage and semiconductor manufacturing are highly concentrated in a few specific geopolitical zones. These global materials funnel into a single ultimate choke point, TSMC in Taiwan. TSMC, or the Taiwan Semiconductor Manufacturing Company, currently dictates global AI capability from a single geopolitically vulnerable island. During the semiconductor shortage of 2021 to 2023, automotive production halted and industrial automation stalled. It proved that these global systems are deeply physically coupled, even when the software narrative makes those connections invisible. Any nation or corporation that treats AI capability purely as an engineering and talent problem, while ignoring its materials and fabrication dependencies, is building its entire future directly on an exposed geopolitical fault line. We already have historical proof of what happens when massive computation scales without physical alignment. Look at proof-of-work cryptocurrency. Proof-of-work is a consensus mechanism that intentionally converts energy into cryptographic computations to secure a digital ledger. At its peak, the Bitcoin network consumed more annual energy than the entire country of Argentina. It generated no materials, no infrastructure, and no scientific knowledge. When you decouple computational intelligence from physical productivity, the incentive structure defaults to pure energy extraction with zero societal output. For a macrosystem example, look at Germany's energy transition, the Energiewende. Following the Fukushima disaster, Germany decided to abruptly alter its energy generation mix, phasing out massive amounts of nuclear power. But they did this before securing grid-scale battery storage or geopolitical resource independence. Removing their domestic firm baseload power forced a bridging dependency on foreign natural gas, effectively weaponizing their own energy grid against them. Whether you are maximizing raw computation like crypto or abruptly shifting power generation like Germany, optimizing a single variable of the civilizational equation in isolation produces massive waste and severe strategic exposure. This timeline outlines the strict, non-optional sequence a civilization must follow to reach an energy-constrained intelligence era. We are currently in Phase 2, constraint exposure. Grid limits are becoming obvious, and supply chains for critical minerals are tightening. We are rapidly approaching Phase 3, system stress. The constraints will produce severe economic signals. Expect energy price volatility, persistent inflation in power-intensive sectors, and direct geopolitical conflict over resource routes. The prevailing narrative in Silicon Valley assumes we can bypass these stressors by reaching Phase 5, breakthrough readiness. They bank on unlimited energy abundance from commercial fusion or advanced geothermal technology. The physics of those energy breakthroughs are completely sound, but the engineering required to deploy them at a global scale is decades away. You cannot skip Phase 4. Phase 4 is alignment emergence, the actual deliberate work of designing efficiency-first AI, distributing grid systems, and building resilient supply chains. Injecting unlimited energy abundance into a fragile, unaligned system does not produce a utopia. It simply accelerates the destabilization of the civilization at a much higher amplitude. Systemic stress does not naturally birth equitable solutions. When historical crises force a correction, they typically entrench power asymmetries, leading to energy rationing and authoritarian capture. Surviving this transition requires deliberate, preemptive institutional design. We have to build the architecture before the crisis hits. That starts with circuit breakers. We need governance mechanisms capable of pausing capability development the moment energy demand exceeds defined grid capacity thresholds. Next, we need strict AI energy intensity disclosures. Forcing developers to transparently report the energy footprint of their models creates direct market pressure for architectural efficiency, without dictating exactly how the engineers solve the problem. To test these concepts safely, we need local alignment sandboxes, controlled geographic zones where new integrated energy and AI models can be deployed and evaluated at scale. Iceland serves as a primary example of this. Their unique geography provides a natural sandbox where abundant, low-entropy geothermal energy is directly matched to computationally intense workloads, minimizing waste and transmission loss. India offers another exportable model. Rather than maximizing raw capability, their policy playbook focuses AI deployment specifically on optimizing their complex electrical grids and improving agricultural energy efficiency, actively closing the gap between intelligence and power. Negotiating a global treaty on AI alignment will take decades, but these modular, bottom-up sandboxes prove that exponential systems can be coherently governed right now. In the 20th century, superpowers were defined by their ability to control physical energy choke points. Oil and gas pipelines were the substrate of geopolitical leverage. In the 21st century, the substrate of power has moved from the control of liquid fuel choke points to the management of compute-ready energy. Neither the total count of graphics processing units nor the top scores on model benchmarks will determine global dominance in the coming era. The next superpower will be the civilization, block, or network that successfully sustains exponential intelligence under the strict constraints of physical reality. That requires the unglamorous work of Phase 4, building resilient supply chains, deploying distributed energy architecture, and demanding democratic accountability for resource allocation. The future will not be determined by who can build the most powerful system. It will be determined by who can build a system stable enough to actually last.